Good evening, Lamai. So, let's start the session. වැඩි පටන් ගමු right මම හිතනවා මේ ඔයගොල්ලන්ට ටියුට් එක හම්බ වෙන්නද කියලා. right ඒකේ copy එකක් ගන්න. right next week මම try එකක් දෙන්න ටියුට් එක දෙන්න. හරි. Okay, so let's start the lesson then. Right, this is about the solubility product, or which is also known as the KSP equilibrium. Right. Here we are going to discuss about the systems with precipitates, right? Aqueous solutions containing precipitates, right? Those are the main stuff available with this session, right? So let's go to the session then, right? So this is about the solubility product, right? First of all, attitude, right? They have mentioned about the solubility of ionic as well as covalent compounds in water, right? So how they are supposed to dissolve in water. So when it comes to ionic compounds, they dissolve in water by forming ions. They ionize and get dissolved in water. And that is how the ionic compounds will dissolve in water, right? So this equilibrium is always regarding the aqueous solutions, right? Okay, when it comes to ionic compounds, they dissolve in water by forming ions, right? Like this. When it comes to ionic compounds, dissolved in water by forming ions, right? Like this. So NaCl is kind of ionic compound. So if you add some NaCl to water, right, that will form ions like this. So they will ionize, dissolve in water, right? But when it comes to covalent compound, right, dissolves with the formation of normally the hydrogen bonds with water molecules. Dissolve in water by forming H bonds with water molecules. You won't see any kind of ions occur in there, right? See, when it comes to glucose, right? Sorry, that thing will dissolve in water like this. Just forming hydrogen bonds with water molecules, right? So just the molecular form appearing. Here, when ionic compounds are dissolved, ions are formed. Here, just the molecular form appearing. Right? So we can say, right, when ionic solutions are dissolved in water, the solutions behave as strong electrolytes. Solutions behave as strong electrolytes. Right? These solutions are referred to as strong electrolytes. So electrolyte is something which can conduct electricity. So with the solutions containing ions, you can conduct electricity as charged particles are there, right? You can carry the charge from one point to another point using the charged particles, right? So with ionic solutions, you can think of them as strong electrolytes. But here, these are considered as weak electrolytes, or we can say insulators, right? So one can say non-electrolytes. You can't conduct electricity with these covalent solutions. Right? No ions, no charge carrying particles are there. So that is what mentioned at the first point. Right? In this section, with the solubility product equilibrium, we are referring to these kind of stuff. Ionic compounds. We are not referring to covalent compounds, but we are referring to ionic compounds when it comes to solubility product equilibrium. Right? Okay. Right. Then when it comes to ionic compounds, the strong electrolytes, right? Some ionic compounds dissolve greatly in water, but some do not. Right? Some ionic compounds dissolve greatly in water, but some do not. Right? Some guys are not dissolving that much in water. Those are the ones we can observe as precipitates in our precipitation table. So in our inorganic chemistry lessons, we had discussed about the precipitation table. No? There are three kinds of salts have appeared. No? Three kinds of ionic compounds were there. No? Some ionic compounds were there, which are referred to as soluble stuff, complete dissolves in water. And some ionic compounds were there, which are known as precipitates, like barium sulfate, magnesium carbonate, those carbonates, precipitates, insoluble stuff. And some were there, referred to as slightly soluble. So see, when it comes to ionic compounds, even though if they are to dissolve, they will come up as ions, still, according to the amount of right dissolution, the ionic compounds are of three types. Some greatly dissolves, which are known as soluble compounds. Some very hardly dissolves, which are known as insoluble or precipitates, and some are with some moderate dissolving nature, which are also known as slightly soluble stuff, right? So, when it comes to ionic compounds, there are three categories according to dissolution in water, right? According to extent of dissolution, right? Ionic compounds fall into three categories. Right? Category 1, category 2, and category 3. Right? Category 1. Right? Which are known as soluble ionic compounds, which are known as soluble ionic compounds. When it comes to their solubility, right? The solubility is actually greater than 0.1 moles per decimeter cube, right? In 1 liter of solution, in 1 liter of water, more than 0.1 moles of the ionic compound will dissolve, right? In 1 liter of solution, more than 0.1 mole of compound will dissolve. Those are referred to as soluble ionic compounds. If you need an example, NaCl is such. In a precipitation, it is referred to as a soluble compound. Right? The category 2. Category 2, slightly soluble stuff. Slightly soluble. When it comes to their solubility, the solubility is greater than 0.01, right, but less than 0.1, right. If you need a kind of a example for those, right, we can think of kind of calcium sulfate. Calcium sulfate comes under slightly soluble, SS, right. Then the category 3, which are known as insoluble ionic compound, where their solubility is less than 0.01 moles per decimeter cube. 0.01, less than 0.01 moles will dissolve in 1 liter of water. So if you need an example, barium sulfate, your precipitates are the best example for insoluble stuff, right? In this lesson, we are mainly focusing on these guys. Category 3, the insoluble stuff, where we could observe precipitates, where we could observe precipitates. Precipitation occurs with those stuff, right? Okay. So solubility at equilibrium is all about dissolve in these insoluble stuff in water, right? Okay. When it comes to these kind of stuff, right? Kind of equilibrium between the solid ionic compound and aqueous ions would appear. Kind of a equilibrium between solid ionic compound and aqueous ions would appear. See, how could it be, right? These are some general stuff, right? You should know some theory parts. Actually, this is referred to as kind of a calculation lesson, but very few theory parts to be learned, right? So, when considering insoluble, that means precipitating, ionic compounds, the following equilibrium appears. Right? It's like this now. If you are trying to dissolve, if you are to add some barium sulfate solid to water, let's say to 1 decimeter cube of water, so this kind of thing will happen. So barium sulfate solid, but to adding will dissolve with a very lesser amount. This only means will come to the aqueous solution, come it as aqueous ions, very little amount. It's like, right, if you are to add some barium sulfate solid, right, only kind of 0.01 moles may dissolve, very little amount, right? So basically less than 0.01, that means let's say 10 to the power minus 4 moles may dissolve in 1 liter. very little stuff. Let's say you are adding some 10 moles there, 10 moles there, just 0.0001. Very little amount will dissolve. Very little amount will dissolve. See, very little amount will dissolve. But all the dissolving molecules will completely convert to ions. Completely convert to ions, aqueous ions like this, right? Very little amount will dissolve. Very little amount will dissolve, so that kind of a solid stuff will appear. Barium sulfate solid will appear. Very little amount will dissolve. But all the dissolved stuff will completely convert to ions, forming 10 to the power minus 4 moles of barium 2 plus and 10 to the power minus 4 moles of sulfate. That means all of the dissolved solid will totally convert to the two ions. So nothing will appear like this at the aqueous form. Completely ionized. You can say completely ionized. Partial dissolves or slightly dissolves, but all dissolved molecules will completely ionize. So that we will observe kind of equilibrium between the solid and the aqueous ions. We will observe some equilibrium between the solid and the aqueous ions. Right? This is the equilibrium we are concerning with the KSP, with the KSP stuff. Clear? Right? So for this equilibrium, this kind of equilibrium, we can write a K value. We can write a K value. So K is equal to barium 2 plus sulfate divided by barium sulfate solid. But we know this is going to be a constant, the solid, the container of solid. So we can write this thing as K into barium sulfate solid is equal to barium 2 plus aqueous and the sulfate aqueous. So this constant is what we refer to as the KSP. As we know that constraint of a solid is a constant and K is always a constant. So this is what we known as refer to as the KSP, right? So we can write the KSP expression between the solid and the ions, respective ions, aqueous ions. We can copy the KSP expression like this. The KSP is equal to the two ions barium 2 plus and the sulfate 2 minus. Right? This is the KSP expression. Right? So that is this is how it is derived. Right? Clear? No? Very simple stuff. Right? This is how we are deriving the KSP expression. Right? So basically, it is all about the equilibrium existing between the solid precipitate and the aqueous ions. So even without writing the equilibrium reaction, still you should be able to come up with the equilibrium expression. See how we are supposed to write the equilibrium expression even without writing the equilibrium reaction. These are clear. All of these are appearing in your note, right? Nothing much to worry, right? So even without writing the equilibrium, we should be able to come up with this expression, right? It is not hard, lava. It's like KSP is equal to KSP is equal to, when it comes to barium sulfate, you have one Ba2 plus ion and one sulfate ion, just one ions, right? So one Ba2 plus and one sulfate ion, just one as a stoichiometric value. So that power should be one, right? So this is the KSP equilibrium. So as a definition, we can say it is the product. It is the product of respective ions. It is the product of respective ions. It is the product of respective ions in a saturated solution. In a saturated solution, right? It is a product of respective ions of your salt in a saturated solution, right? This solution is referred to as saturated solution. I'll explain that thing why it is referred to as that, right? This solution is referred to as saturated solution, right? Saturated solution. So you can define the KSP as the product of concentration of respective ions of the salt in a saturated solution. In a saturated solution, the product means the multiplication of concentrations of the considering corresponding ions, right, of a considering salt in a saturated solution can be referred to as the KSP. See, it is written there, right? You can go to the point there, right? So it is said, right, at the next page, it is said KSP is called as a soluble product constant, and KSP is defined only for saturated solution. We'll discuss what the saturated solution means, right? Next, at the next time, I will discuss, right? So this is the idea of the KSP, right? Right now. Okay, let's discuss a bit about what are these saturated solutions, right? Let's discuss to have some great idea about the applications. You should know about what the saturated solution means, right? Okay, so to come up with some idea about saturated solutions, I'll explain you a thought experiment, right? I'll come up with a thought experiment, right? So then we can have some great idea about this concept of saturated solutions, right? Okay, so KSP is always applied for saturated solutions. If you need an example for saturated solution, right? Any solution appearing with a precipitate, any aqueous solution appearing with a precipitate can be referred to as a saturated solution of that precipitate, right? So see the concept of saturated solution. Concept of saturated solution, right? Let's think of this situation. Say you are with a pure water. You are with a right beaker with pure water, and let's say you are adding some barium sulfate molecules one by one. You are adding barium sulfate molecules one by one, just one by one, to this aqueous solution. Let's see. Let's think of such a thought experiment there. You are adding barium sulfate compounds, I mean molecules, one by one to water. So what will happen? So it's solid, right? One by one molecule at a time, right? So when you are to add the first molecule there, what will happen? The two ions will, when it comes to solution, that guys will ionize like this. Two ions will come to the solution and will appear as aqueous ions, as water molecules will surround it. Water molecules will surround, come to those Ions will surrounded by water molecules, right? So if you add the second molecule of barium sulfate, again that is what happens. The two ions will be surrounded by water molecules like this. I'm adding third molecule as well. So again the same thing will happen, right? Water molecules will surround these ions, right? These ions will be surrounded by the water molecules, right? Third ion, third instance. Like that, when you are adding the barium sulfate molecules one by one, little by little, this solution become crowded. And at one instance, when you are adding like that one by one the barium sulfates, at one instance, right, these ions get so much closer, get so much closer, where it could attract to each other, where it could attract to each other, so that precipitation would occur, right? At some instance, when you are adding molecule by molecule, at some instance, this solution will be so much crowded such that the ions will come much closer, right? And they will precipitate there, right? So before the addition of that last barium sulfate molecule, the solution is said to be a saturated solution, right? Before the addition of this last barium sulfate thing, where the ions get started to precipitate, that solution is referred to as a saturated solution. So it can be referred to as a solution containing the maximum amount of ions can be there as aqueous ions, right? So this situation is called as saturated solution, right? Just before the start of precipitation, the solution is referred to as a saturated solution. It can be defined as a solution containing maximum amount of ions which can appear as aqueous ions. So a solution containing maximum amount of ions which can appear as aqueous ions can be referred to as saturated solution. After saturation solution, if you are adding just one molecule to a saturated solution, what will happen? That molecule will get precipitated because the solution is now saturated with aqueous ions. If you are adding further ions to the solution, those can't be there as aqueous ions, then those will get precipitated and will go to the solid state. That is what happens, right? So if you have to add some just one molecule, what will happen is those ions can't be there as aqueous ions because maximum allowed amount is there as a saturated solution. So those will get precipitated, right? So this is the situation of saturated solution, right? The solution just before the start of precipitation is referred to as saturated solution, right? So a solution containing maximum amount of ions which can appear as aqueous ions can be referred to as a saturated solution, right? So if you are adding further, if you are adding further molecules after the solution is saturated, what happens is those molecules will get precipitated. Will get precipitated. See, these two guys will get precipitated like this. So remember, so remember, even with precipitate as well, you would observe a saturated solution. So solution becomes saturated. Solution will become saturated just before the start of the precipitation, and afterwards also, if you are at some molecules, still the solution is saturated, right? So only if the solution is saturated, you are able to see a precipitation. හරි පැහැදිලි නේද? හරි. precipitate එක හැදෙන්න හරි පොඩි වෙලාවකට precipitate හැදෙන්න ඔන්න මෙන්න අවස්ථාව තමයි saturated solution එකක් කියලා කියන්නේ. saturated solution එකක් කියලා කියන්නේ ඔයාට aqueous science විදිහට තියාගන්න පුළුවන් maximum allowed ions amount එක ඉන්න වෙලාවට. ඊට පස්සේ ඔයා එක molecule එකක් හරි add කරොත් solution එකට මොකද වෙන්නේ? ඒක ඔයාට aqueous science විදිහට contain කරන්න බෑ system එකේ. ඒක නිසා යා solid form එකට convert වෙනවා. Right? So the solid, the precipitate occurs when you are with a saturated solution. Without a saturated solution, you can't think of a formation of a solid. Formation of precipitate, right? So, මම කියන්නේ saturated solution එකක් කියන එක. ඒක කතා කරොත් that is the situation where you have the maximum amount of ions can be there as aqueous ions, and such a solution will appear just before the start of the precipitation as well as with a precipitate, right? හරිද? ඒක තමයි consider saturated solution. So the KSP stuff apply for these solutions, saturated solutions, right? When considering saturated solution, the multiplication of these two ions, see, barium 2 plus ions, the considering of barium 2 plus ions, and the sulfate ions. The multiplication of considering of these two ions of saturated solution is going to be a constant, and which is known as the KSP. Right now, that is what KSP means. Got the idea? No? Right? මොකද saturated solution එකේ idea එක වලන තියෙනවා. පැහැදිලි නේද? හරිද ළමයි? හරි. එහෙනම් අපි බලමු මේකෙන් කොහොමද questions එන්නේ කියලා. මම කියන්නේ පොඩි idea එකක් තියෙනවා දැන් ඔයාලා කොහොමද saturated solution එකක් හැදෙන්නේ සහ saturated solution එකට apply කරන්න පුළුවන් equation එක ගැන යම් කිසි idea එකක් දැන් ඔයාලට තියෙනවා. Right? හරි. අපි බලමු එහෙනම් මුලින්ම මේ KSP expression එක ලියාගන්න හැටි පොඩ්ඩක් try කරමු. Right? ඔයාගේ page number 2 එකේ you have a question there. Right? Saying write the equilibria exist in following saturated solutions and write the respective KSP expressions. Right? Let's do that exercise. Right? That is all about writing KSP expressions and the equilibria, right? The question is write the equilibria. And KSP expressions. Right? For saturated solutions. Of following systems. With precipitates. Right? So these are the stuff they have mentioned. Magnesium hydroxide, number 2 barium phosphate, number 3 chromate. See, so I like it here. Let's try to come up with the equilibria as well as the KSP expressions. So for magnesium hydroxide, how to come up with equilibria? So equilibria can be written like magnesium hydroxide, solid, double arrow. When it dissolves, it will form one of magnesium 2 plus ions, the magnesium 2 plus and the OH minus. So 1 of magnesium 2 plus ion equals and 2 of OH minus ions, 2 of OH minus ions. Right? And how about the KSP? So KSP can be written like as KSP is equal to, first write the two ions, magnitude 2 plus and the OH minus. First write the two ions there. You should be able to write the KSP by just looking at this chemical formula, right? No need of knowing the equilibrium there. By just looking at the chemical formula, you should be able to write the KSP expression. So you are with magnitude 2 plus signs and the OH minus signs, magnitude 2 plus signs and the OH minus signs. So those are the two ions with the system. And just one magnitude 2 plus sign and two OH minus signs, two OH minus signs. So just one magnitude 2 plus and two OH minus. So this is how the KSP equilibrium is written. One magnitude 2 plus signs and two OH minus signs. Two OH minus signs. See? Let's come up with the barium phosphate thing as well. First, let's write the equilibrium there. So if barium phosphate to dissolve, the solid to dissolve, it will form 3 of barium 2 plus ions, barium 2 plus, PO4 3 minus, PO4 3 minus, barium 2 plus. So 3 of Ba 2 plus ions are there. 3 such ions are there. And 2 of phosphate ions, 2 of phosphate ions. So how to copy the KSP expression there? So KSP can be written as, first write the two type of ions there, Ba2 plus and PO4 3 minus. First write the two types of ions, the concentrations, Ba2 plus and then PO4 3 minus. Then how many? So you are with 3 of Ba2 plus ions, 3 of Ba2 plus ions, 3 such 3 ions are there. So 3 ions are there. And 2 phosphate ions, 2 phosphate ions, 2 ions are there. So that is how the KSP is written with the barium phosphate. Right now? So let's try to come up with the silichromate as well. First let's write the equilibrium there. It is Ag2CrO4 solid, double arrow giving you 2 of Ag plus ions and 1 of chromate ions. Right? So let's come up with the KSP. So KSP is equal to, first write the two ions, Ag plus and the chromate ions. First write the two ions, Ag plus and the chromate ions. Then come up with the numbers. So 2 of Ag plus ions are there, 2, and just 1 of chromate ions is there. So that is 1. So that is how the KSP expression is written. Right now? So you should be able to write the KSP expressions as well as the KSP as well as the solubility equilibria when a compound is given, ionic compound is given. Right? And remember, this KSP appears only with the saturated solutions. Right now? Let's complete this stuff level. Right now? So let's come up with the applications of this concept. So as theory, we are going to learn about 4 types of applications. 4 types of applications with the KSP. So let's start with the first type of application here. Right? right? The applications, right? So in a note, those are referred to as special topics in under KSP, special topics under KSP. Special topics, right? Topic number one. So we can use the concept of KSP to predict whether precipitation will occur or not. When you are mixing two salts, to predict whether precipitation will occur or not, we can use the concept of KSP, right? So this is about predicting the formation of a precipitate. The formation of a precipitate. Predicting the formation of a precipitate. That is the first thing. Right? So let's discuss a bit about this situation. Lavine, let's say like this, right? So if you are adding some two salts, let's say that you are adding some barium chloride and sodium sulfate. You are adding some barium chloride and sodium sulfate. And what we are assuming is, what we are predicting is kind of a formation of barium sulfate precipitate. Barium sulfate precipitate, right? So if the two things are added, with 0.1 mole, with 0.1 mole or greater than that, if the two things are added with 0.1 mole or greater than that concentrations, then a precipitation will definitely occur. Precipitation will definitely occur. Say the content of barium 2 plus adding here is 0.1 and the content of sulfate times adding here is 0.1, then definitely a precipitation will occur. If the two things are adding are with concentrations 0.1 or greater than that, we say definitely a precipitation will occur. But if any one of those, if any one of those are coming up with concentrations less than 0.1, less than 0.1, see 0.001 like that. If even one of those coming up with a concentration less than 0.001, then we have to perform a calculation. We have to perform a calculation to confirm whether precipitation will occur or not. Right? To confirm whether precipitation will occur or not, we have to perform a calculation if at least one of those are with some concentration less than 0.1, right? So now we are going to discuss how such a calculation can be performed, right? That is the discussion here, right? See, in a note it is written. Just go to the first 2 points there. Any compound having low solubility will precipitate if the concentration of both the ions are 0.1 molar or higher. Right? The second point says, however, if the concentration of at least one ion is less than 0.1 molar, a calculation must be performed to predict the formation of the precipitate. To predict the formation of a precipitate. Right? So that calculation is named as the ionic product calculation. That calculation we are supposed to perform is referred to as the ionic product calculation. Right? So let's discuss how this kind of a calculation, the ionic product calculation, is done to predict whether the precipitation will occur or not. Right? So the idea is this. So to perform this kind of calculation, right, first we should know what this ionic product means. What this ionic product means. Ionic product means. So ionic product. Let's discuss a bit about the ionic product. What this means. Right? What this means now. Right? So ionic product. Ionic product means, which is known as the IP. IP is actually a measure of. It's a measure of total amount of ions. Total amount of ions of interested ions added to the system. Ion product is a measure of total amount of interested ions added to the system. In this case, our interested ions are the barium 2 plus and the sulfate ions. So ionic product is a measure of total amount of interested ions added to the system. Right? And what that KSP means, what this KSP thing means. Earlier we had discussed what that means. KSP means it's a measure of maximum amount of ions maximum amount of interested ions that can appear as aqueous ions. Right? So ionic product means a measure of total amount of interested ions added to the system. KSP means a measure of maximum amount of interested ions that can be appear as aqueous ions. So we can say if IP is less than the KSP, if IP is less than the KSP, we can say it's like this. No, IP means the total amount of ions added to system is less than the maximum amount of ions that can appear as aqueous ions. The total amount of ions added to the system is less than the maximum amount of ions that can appear as aqueous ions, so that all the ions will appear as aqueous ions. All the ions will appear as aqueous ions. So let's say, so KSP value is 10, IP value is 5. Let's say like that, or 6 or something. That means you can have 10 ions, maximum of 10 ions as aqueous ions. You can have maximum of 10 ions as aqueous ions. But you have added only 6 ions to the system. So all the 6 will appear as aqueous ions then. Only if you are adding more than the maximum allowed as aqueous ions, then only kind of precipitation would occur. Right? But if you are just adding less than the number, than the maximum allowed ions as aqueous ions, all of those things will appear as aqueous ions. So no precipitated will occur. So no precipitated will occur. So this simply means the amount of ions you have added to a system is less than the maximum amount of ions allowed as aqueous ions. So that all the ions will appear as aqueous ions. So if the IP is equal to KSP, that means the number of ions you have added, let's say it's 10, your KSP is also 10. Number of ions you have added to the system is 10. The maximum allowed as aqueous ions is also 10. So all the 10 ions will appear as aqueous ions, and that situation is referred to as the saturated solution. Saturated solution. Now you are containing the maximum amount of ions allowed as aqueous ions. So this is referred to as saturated solution. Just a saturated solution will appear. Saturated solution will appear. So if you are adding more ions than the maximum allowed as aqueous ions, see, if your IP is greater than the KSP, that means let's say the KSP is 10, maximum allowed ions as aqueous ions is 10. You are just adding 12 ions to system. Then what will happen? 10 will appear as aqueous ions, and the rest, the other two, will get precipitated. So 10 will appear in the aqueous solution, creating a saturated solution, and the excess you have added than the maximum allowed as aqueous ions, that means that excess 2 ions will get precipitated, right? So by performing an IP calculation and comparing the IP product with the KSP value, you can predict whether a precipitation will occur or not. If your IP product is less than the KSP, no precipitation. If the IP product is equal to KSP, you will come up with saturated solution, but no precipitation yet. And if your IP product, the number of ions you have added to the system, is exceeding the number allowed as aqueous ions, the rest will get deposited or get precipitated. So precipitation will occur when the IP is greater than KSP. So comparing the IP with the KSP, you can predict whether precipitation will occur or not. Let's do an example to get some clear idea about this thing, right? So I'll do the first question. Appearing in your tute, right? So that you get a clear idea about this concept, right? It is all about comparing the IP product with the KSP, right? So it is just like the QP KP calculation. It is just like the QP KP calculation level, right? This is IP and KSP, right? Let's do the first question there, right? Question number 1. Let's do the question number 1 to get some idea, right? So what they are doing? Is, right? They are adding magnesium nitrate and potassium carbonate. So the two salts which are adding to the system are the magnesium nitrate and potassium carbonate. The amounts are going to be like 42.3 molar. How many? 50 cubic centimeters. The potassium carbonate amount is 1 into 10 to the power minus 2 molar, right? 50 cubic centimeters, right? And the KSP value of the precipitate we expect is given as Ksp of magnesium carbonate. That is what we are expecting as a precipitate. That is what we are expecting, right? Because nitrates never involved in precipitation and K plus never involved in precipitation, right? So magnesium 2 plus ions and the carbonate ions are the two ions to consider for the precipitation, right? So that Ksp value of calcium carbonate is given, which is given as 3.5 into 2.8 mole D minus 3. Let's perform kind of a ion product calculation to predict whether precipitation will occur or not, right? So to come up with the ion product calculation, first of all, let's come up with the concentrations of the two interested ions. The two interested ions are the magnesium 2 plus and the carbonate ions, right? Those are the ions which we are expecting to get precipitated, right? So let's come up with the concentration of the magnesium 2 plus ions at the final solution. This final solution, right? Magnesium 2 plus and the carbonate ions. Those are the two stuff we are considering, right? And final solution is coming up with 50 plus 50, 100 cubic centimeters, right? Let's come up with cyanide product preparation for this solution, right? So magnesium 2 plus concentration. So magnesium 2 plus are adding from here. So amount is 5 into minus 3, that is the concentration, to minus 3. And volume is 50, but now inside 100, now inside 100. This is the concentration, right now? 5 into minus 3 into 15 into minus 3, that is the number of moles, divided by 100 into minus 3. So 10 minus 3 will cancel off, so I am not writing that. So this is the inverse concentration, right? This will cancel off. That is going to be 2.5 into 10 minus 3. Let's copy the carbonate concentration as well. The concentrations of two insulated ions, first of all, to perform ion product calculation, right? The carbonate amount we are adding is 1 into 10 to the minus 2 into 15 to the minus 3 CV, right? CV 15 to the minus 3 divided by 100 into the minus 3. So 10 to the minus 3 will cancel off. So 1 into 10 to the minus 2 into 50 divided by 100, right? This amount of moles, now we are inside 100 cubic centimeters, right? So this is going to be just 2. So 0.5 into 10 minus 2, that means 5 into 10 to the minus 3. Right? So now let's copy the ion product. So ion product of magnesium carbonate. Ion product of magnesium carbonate. Right? So ion product is written like this. So you have magnesium 2 plus ions and carbonate ions. You have just one of magnesium 2 plus, so just one here, just one carbonate here, just one here. Like how we are supposed to write the Ksp, the ion product is also coming up with the same kind of expression. So it is like QPKP, it is like QCKC, coming up with the same kind of expressions. So IP as well as KSP, both are coming up with the same type of expressions, right? So this is the ion product, right, of magnesium carbonate. So let's apply the values. Magnesium 2 plus value is 2.5 into 2 power minus 3 into this value, carbonate value is 5 into 2 power minus 3. So ion product is going to be is 12.5 into 10 minus 6. So it is going to be 1.25 into 10 minus 5. That is the IP value. So you clearly see that IP value is greater than the KSP value. So now you can see the IP value, which is 1.25 into 10 to the power minus 5, is greater than your KSP value, which is 3.5 into 10 to the power minus 8. So the amount of total amount of ions you have added to the system is greater than the maximum amount of ions allowed as aqueous ions. So you have added more ions than the maximum allowed amount, so that the rest will get precipitated. The rest will get precipitated. So the amount of ions you have added to the system is greater than the maximum amount of ions which can be there as aqueous ions. That is KSB, right? So you have added more ions than the maximum allowed as aqueous ions. So the rest will get precipitated, right? So we can say magnesium carbonate precipitates, right? Now that is how an ionic product calculation is performed, right? Now, so just do the second and third questions as well, right? And predict whether precipitation will occur or not. Right? I have just done the first question. So you can copy this one and then do the second and third questions as well at the page number 2. Just perform those calculations as well to predict whether precipitation will occur or not. Just do those. Let's do the second question then, right? Let's do the second one. Question number 2. See what they are doing. So they are adding kind of calcium chloride and sodium sulfate. They are mixing calcium chloride and sodium sulfate. What are the amounts? 1 into 10 power minus 3 molar. How many? 50 cubic centimeters of calcium chloride and right 1 into 10 minus 2 molar 50 cubic centimeters of sodium sulfate added, and we are expecting kind of precipitation here. So ultimate solution coming up with 100 cubic centimeters. 100 cubic centimeters. And what is the precipitate we are referring to? So sodium plus never participate in precipitation. So cation not involving with this one means anion is not involving with the other one. So we are here looking for the precipitation of calcium sulfate. The two interested ions are calcium sulfate, calcium 2 plus and the sulfate ions. So the Ksp value is also given for the calcium sulfate as 2.4 into the power minus 5. Right? Let's see. Let's perform a ion product calculation and see whether precipitation will occur or not. Right? So let's first come up with the calcium 2 plus concentration here. So amount of calcium 2 plus is 1 into the power minus 3 into 50, that is the number of moles, CV, right? Now inside 100 cubic centimeters. So the concentration is going to be 0.5 into 10 minus 3, that means 5 into 10 minus 4. Then let's come up with the other ion, sulfate ion. So amount of sulfate added here, 1 into 10 minus 2 into 50, that is the number of moles, CV, right? Divided by now inside 100. Now inside 100. This amount of moles now inside 100 cubic centimeters, right? This amount of moles inside 100. It is going to be 0.5 into that thing, that means 5 into 10 to the power minus 3. So if you have to come up with the ionic product, here we are referring to calcium sulfate, no? Referring to calcium sulfate, no? So ionic product is equal to the two ions, calcium 2 plus ion and the sulfate ion, two ions, and raised to the power of their number, just one calcium 2 plus ion, just one, and just one sulfate ions, just one, right? So let's multiply the numbers, right? Calcium 2 plus value is 5 into 2 power minus 4 into sulfate value is 5 into 2 minus 3. So the value is 25 into 2 minus 7, that means 2.5 into 2 power minus 6. So IP value is less than the KSP value. So IP value is 10 to the power minus 6, KSP value is 10 to the power minus 5. So this value is smaller than this value. So you can say, so your IP V is 2.5 into 10 to the power minus 6 is less than the KSP V is 2.4 into 10 to the power minus 5. So the total amount of ions, interested ions you have added to the system is less than the maximum allowed as aqueous ions. So all the ions will appear as aqueous ions. So you are adding some less number of ions, right, compared to the maximum allowed number of ions as aqueous ions. So all will appear as aqueous ions. right? So no precipitation will occur there. Calcium sulfate, not precipitating. Calcium sulfate is not precipitating, right now. So no precipitation there, right? That is how that calculation is done with the Roman number with the question number two, right now. Okay, let's do the working. If you got it wrong, and then try the third one. Right. Let's move to the next one. Question number three. Question number three. See what they are doing there. So you are mixing aluminum sulfate and NaOH, no? You are mixing aluminum sulfate and NaOH. Aluminum sulfate and NaOH. What are the concentration volumes? 1 into minus 3 molar. Volume is 50. With this one, so 1 into minus 2 molar is also coming up with 50 cubic centimeters. We are expecting to predict whether precipitation will occur or not after mixing these two solutions. So we are coming up with just 100 cubic centimeters. And what are the two interested ions here? What are the two interested ions here? So Na plus never participate in precipitation. So if the cation is not involved, we no need to consider the anion there. So the two interested ions for a precipitate is the Al3 plus from here and the OH minus from here. Aluminium hydroxide is our concern here. So Ksp of aluminium hydroxide should be given. That is given as 6.3 into 10 to the power minus 32. So let's first come up with the two concentration of the insulated ions. So first the Al3 plus. So amount of Al3 plus here. So 1 into 10 to the power minus 3 into 50, 1 into 10 to the power minus 3 into 50 is the amount of aluminium sulfate we are dealing with. Is the amount of aluminium sulfate we are dealing with. But one aluminium sulfate contain contains two Al3 plus ions. Two Al3 plus ions. One aluminium sulfate contains two Al3 plus ions. So the amount of Al3 plus is twice compared to the aluminum sulfate. So now this amount of moles are inside 100 cubic centimeters. Are inside 100 cubic centimeters. So this is the concentration. Amount of moles inside the volume. So this is just 1 into the power minus 3, no? Then the OH minus concentration. So amount of OH minus you are adding is 1 into the minus 2 into 50. Now this amount of moles are inside 100 cubic centimeters. 100 cubic centimeters. So that is the concentration. It's just 2. That means 0.5 into 10 to minus 2. That means 5 into 10 to minus 3. Right? Then let's come up with the ion product calculation. So this is referring to ALOH3. So the IP of ALOH3 is going to be just the Al3 plus ions, the two component ions, right? And the OH minus ions. Those are the two ionic components in ALOH3. And you have one Al3 plus ion and 3 of OH minus ions. So 3 of OH minus ions, right? Okay. This is the ionic product expression. So let's apply the numbers there. So you have 10 to the power minus 3 moles per centimeter cube into the OH minus number is 5 into 10 to the power minus 3 into 3, right? This is 4, no? So you come up with kind of 5 to the cube 3 cubic value of 5 is 5 into 5 into 5, that is 125. 125 into 10 to the power minus 9 is there and some 3 to the power minus 2. It can be written as 1.25 into 10 to the power minus 10 mole for dm minus 12. So you clearly see your ionic product is a greater value, 10 to the power minus 10 is kind of greater value than the Ksp. Your ionic product is 1.25 into 10 to the power minus 10 is a greater value than the Ksp of aluminum hydroxide, which is 6.3 into 10 to the power minus 32, right? So the amount of ions you have added to the system is exceeding the amount of ions that can be there as aqueous ions. So exceeded amount will get precipitated. So we can say aluminium hydroxide precipitates. Aluminium hydroxide precipitates. Right now? So that is what happens, right? So do the working. Right. Ne? Okay, let's move to the question number 4. With the question number 4 onwards, right, we are going to think of a different aspect of the KSP. Right? Let's discuss a bit about what we are going to discuss with the question number 4 onwards. Right? With the question of 4 onwards, 4 to 8, we are going to see see the KSP thing with a different view. The different view. See what it means. So the KSP is actually KSP is actually KSP is actually the multiplication of the cation. It is the multiplication of considering of the cation and the anion. No? KSP is that no, the multiplication of considering of cation and the anion. In a saturated solution, no? This is what KSP means, no? Right? It is the multiplication. It is actually giving you some idea about the multiplication of two ions representing the precipitate there, the KSP. So one can say KSP is kind of a, one can see this KSP as a three-term equation. KSP can be seen as a three-term equation where the multiplication of two cationic and anionic, two ionic constituents are appearing. Right? So KSP is kind of a three-term equation where you have KSP, the multiplication of the cation, the constituent of the cation in the aqueous solution, and the constituent of the anion of the aqueous saturated solution. Right? So we can say, we can say, or we can use this KSP actually to find out the concentration of the one kind of ion. You can use the KSP to find out the concentration of one kind of ion if the concentration of the other ion and the KSP are given. So KSP is kind of a tool. So KSP is kind of a tool which can be used to find out the concentration of one kind of ion when the concentration of the other ion and the KSP are given. Right? Say they have given the KSP value of the precipitate or the saturated solution as well as the concentration of one kind of ion in saturated solution. So KSP is kind of a tool we can use to find out the concentration of the other ion, because it is a three-term equation. If you know the KSP and if you know the concentration of one ion, it can be used to find out the concentration of the other ion in your saturated solution or in a solution containing the precipitate. Right? So this is the vastly used application with the KSP. Right? It's a tool to find out the concentration of one kind of ion if the KSP and the other ion's concentration is given. Right? KSP is the tool to find out the concentration of one ion in a saturated solution or in a solution with precipitate then KSP and the concentration of other ion is given. Other ion is given, right? So this is the most important application with the KSP, right? So let's use this one to solve the problems appearing with the question number 4 onwards, right? So I'll give you some idea. With the fourth question. I'll do the fourth one to get the idea of what I'm telling here, right? So first, try this thing in your notes. KSP is a tool, is the tool. KSP is the tool. KSP is the tool, right? To find out the concentration of one ion, if the concentration of other ion and the KSP are given, right? So let's see how to use this one, right? Let's come to the question number 4. Right? Okay, see what it says. What is the maximum SR2 plus concentration that can exist in a 0.2 mole solution of K2SO4 without forming a precipitate of strontium sulfate? So what they are asking, right? They are asking this kind of question. So you have a solution with some SO4 2 minus concentration which is equal to 0.02 moles per degree cube, and they are asking you about the strontium 2 plus concentration, strontium 2 plus concentration, and they are providing you the KSP value of strontium sulfate. They are providing you the KSP value of strontium sulfate given as 3.2 into 10 to the power minus 7. Right? They are asking the maximum strontium 2 plus concentration that can exist without precipitating in a solution containing 0.02 molar sulfate. So, see how to solve this one. So, what we can do, right? So, if you are thinking of the KSP, solving this thing is very easy. KSP is kind of a 3-term equation, 3-variable equation or 3-term equation, which relates the concentration of two ions with the KSP value, right? So here, actually, the KSP is given and the concentration of sulfate is also given. What they are asking is this. So see, apply to KSP will give you the sulfate concentration easily. So just apply. So 3.2 into the power minus 7 is the KSP value, and the SR2 plus concentration, that is what they are asking, and sulfate ion concentration is given. So this 2 into 10 to the power minus 2. See how easy to come up with the answer here. So if you subject the SR2 plus concentration, so just dividing this thing with here, so that will give you as 1.6 into 10 to the power minus 5. This comes to there. This is the maximum amount of 72 plus ions, second phase of 72 plus ions can appear without get visibility, without get visibility, right now. So with this thing, we are discussing about the most important aspect of KSP, right? It's a three-term equation. It's a three-term equation. So in a saturated solution, when concentration of one ion and the KSP is given, you can use this tool of KSP to find out the concentration of the other ion, right? That is kind of a very important application in KSP, right? So just complete the question number 4 and then try the question number 5 as well. But in this kind of same aspect can be used for the question number 5 as well. KSP is kind of a three variable or three term equation where in a saturated solution, when one ion concentration is given and with the KSP, you can use that tool to find out the concentration of the other ion, right? Okay, see, let's try the question number 5 as well. Let's do the fifth one, right? Fifth question. Question number 5. See what they are saying. What is the maximum pH that can be achieved? pH means you are supposed to find out the OH minus concentration, right? They are asking for maximum pH. Maximum pH. That means what they are asking is finding out the OH minus neither. Finding out the H2O plus concentration or the OH minus concentration, right? That is what they are asking. They are asking for pH. Or you need to come up with the OH minus OH, H2O plus concentration, right? That can be achieved in 0.01 solution with magnitude plus ions without forming the magnesium hydroxide precipitate, right? What they are asking is like this. So you have a solution with magnesium plus ions with some concentration equal to T to the power is 2. T to the power is 2. Right? What they are asking is what is the maximum pH can be achieved without forming the magnesium hydroxide precipitate, right? So they are asking for kind of pH. So pH means that is just the OH minus concentration, right? pH means just the OH minus concentration they are asking. pH is asking, that means OH minus concentration they are asking, right? And the KSP is given. KSP is given for the magnesium hydroxide as 7.1 into 10 to the power minus 12. See how easy the question is. So they are asking for maximum pH. So find out the pH means find out the H2 plus or the OH plus, right? Simple as that. So let's consider our KSP equation. So KSP is equal to, this is for magnesium hydroxide. We are referring to magnesium hydroxide. So KSP is equal to magnesium plus concentration into OH minus concentration squared, right? 2 OH minus ions are there, just 1 Mg2 plus ion and 2 OH minus ions. So actually they have provided the KSP value as well as the magnitude plus value. And this is what we need. So finding out the OH minus will leads you to the POH and then to the pH. The thing is done, right? Very easy. So 7.1 into 10 to the power minus 2, 12. That's the KSP value. Equal to magnitude plus value is given at 10 to the power minus 2. Into OH minus square. So your OH minus squared will come up as 7.1 into 10 to the power minus 10. Then you can come up with the OH minus by taking the square root there. The square root of 7.1. See, that should be a value between the 2 and 3. Square root of 7.1, no? 2.66 minus 5. So as we have found the OH minus concentration, we copy the POH and then the pH. So POH is minus log OH minus concentration, that is minus log 2.66 into 10 to the minus 5 is 5 minus log 2.66. That value is going to be, you can just look at the log book to come up with the log 2.66. that will be given as 0.4248, right? 4248, that is just 4.5752. pH is equal to 14 minus POH, that is 14 minus 4.5752, that is just 9.4248. So 9.42 is the maximum pH you can achieve without precipitating the magnesium hydroxide. If you are increasing the pH than that, your OH mass content will be so high and magnesium hydroxide start precipitating. Right? That is the idea. So anyway, solving the problem is very easy if you can see the KSP as a three-term equation that can be used as a tool to come up with the concentration of the missing ion when the concentration of the other ion and the KSP are given. Right? So that is how we are supposed to solve this one. This is a question number 5. Right? Let's do the working and then try the question number 6 there. Right now, let's do the sixth question. Right, let's try to do the question number 6. These are just applications of KSP, right? Just using the KSP as a tool to find out the concentration of missing iron in the question of other iron as well as the KSP are given. Right? See, question number 6. See what they are saying. An electrolysis process was carried out using 25 cubic centimeters of 1 into 10 power minus 5 molar zinc sulfate solution. Inert electrodes and 1 milliampere current was used. Okay, see what they are referring to. So, electrolysis process was carried out, right? So, you had a solution like this, right? It's kind of zinc sulfate solution. Zinc sulfate take a solution. So, two terminals are there definitely for electrolysis, right? And they had used kind of a 1 milliampere current, right? Inert electrodes are used. Inert electrodes are used, right? Both are inert, right? Carbon or platinum electrodes, right? And zinc sulfate. Now we have a little problem with the question. Just take the solution as zinc chloride. It's better, right? Zinc chloride. Just take it as zinc chloride for the clearness of the calculation. Zinc chloride, right? Zinc chloride, right? Take that zinc chloride, right? So KSP value for some precipitate is given. They haven't mentioned what is the precipitate, but KSP value of a precipitate is given. Right? See what will happen here. The solution was set up like this. See what will happen. Right? Okay. So this is the positive terminal, this is negative terminal. So from negative terminal, the electrons are released. Electrons are released. So this is then going to be the cathode where the reduction occurs. And towards the positive terminal, the electrons are attracted. So that is going to be the anode where the oxidation occurs. Electrons are releasing, that means oxidation. So that is going to be the anode where the oxidation occurs. Right? So what will happen? So basically, the cations in the aqueous solution attracting towards the cathode, or cations will attract towards the negative terminal. Negative terminal. This is negative terminal. To the negative terminal, the cations will attract. The cation, zinc 2 plus. Anions will attract towards the positive terminal. Negative ions will attract towards the positive terminal, right? So and then water is also there in the medium. Water. So water from its positive delta terminal will attract towards the cathode, and water from its negative delta terminal will attract towards the anode. This is what happens. This is how the ions, right, will travel towards the terminals. So let's discuss about the reactions involving the cathode and anode. Right? At cathode, what will happen? Out of the two guys, zinc and the hydrogen, the one which is relatively lower at the active series will get reduced first. So when it comes zinc and hydrogen, hydrogen is lower than zinc in the active series, so that will reduce first. So at the cathode, the reduction will occur with the water. So water will reduce to H2 gas. So if water is involving at the cathodic reaction in a neutral solution, right? So it is considered as kind of a basic medium balancing, right? With a neutral salt, if water is reducing at the cathode, we are supposed to come up with a basic medium balancing, right? So is plus 2, this 0, so 2 electrons are needed here. So to balance the medium, balance the charges, we use the medium as 2 or 4 minus ions, basic medium balancing, right? So 4 hydrogens are appearing, so some 2 here needed. That is the cathodic reaction. What happens at the anode? At the anode, Cl minus and the water are there. So no oxidation is possible with the anodic terminal because those are electrodes. Then we come to the solution. So Cl minus ions are there. So Cl minus will get oxidized there. Cl minus will get oxidized to Cl2 gas. The two of these things needed. So 2 electrons. That is the oxidation. So with time, what will happen? With time, the solution become basic. With the cathode, as OH minus ions are released, the solution become basic with time. At the anode, H plus or OH minus are not released, so only from the cathode the water is hydrolyzing and OH minus is released. So solution become basic with time when the electrolysis process is carried out. So at some instance, when the OH minus are released, that OH minus contained into the zinc 2 plus contained here will equal to its Ksp value, will be equal to its Ksp value. The zinc 2 plus contained is given, right, as 1 into 2 minus 5. So something is given as 1 into 2 minus 5, no? So as OH minus ions are producing, when the process is carried out, there will be an instance at which the OH minus conversion into the zinc 2 plus container, that means the iron product of zinc hydroxide, will achieve its Ksp. At that instance, the precipitation starts to occur. You see the first appearance of precipitate when that iron product equals to the Ksp of the zinc hydroxide, right? So that is the precipitate we are concerning here. So what they are asking is actually calculate the time taken to first appearance of the precipitate. They are asking for the time taken to appearance of the precipitate. So how to calculate that thing? So we know the zinc 2 plus contained here, that is 1 into 10 to the power minus 5. So if you are thinking of the Ksp of the zinc hydroxide, that is the precipitate we are referring to, right? The Ksp value is given, zinc 2 plus value is given, so that with the use of Ksp you can copy the OH minus concentration, right? So Ksp is kind of a 3-term equation which we can use to find out the concentration of one kind of ion when the concentration of the other ion and the Ksp are given. So Ksp is given, Since 2 plus is given, so we can use the KSP to come up with the OH minus solution. As the volume of the solution is given, it is 100 cubic centimeters. As the volume of solution is also given, and as we had found the OH minus from the KSP, those two things can be related to come up with the number of moles of OH minus. Number of moles of OH minus. When the OH minus moles are known, that can be used to come up with the number of moles of electrons. So that can be related to charge passing through the external circuit. Q is equal to NF. So that will lead to the time with the Q ID. That is how we are supposed to solve the problem, right? Let's solve that thing step by step, right? The first thing we are doing is finding out OH minus continuum. When or at the first instance of appearance of zinc hydroxide precipitate. So you can use the KSP there. So the KSP value is 4 into 10 to the power 17, right? Zinc 2 plus value is given as 1 into 10 to the power 5. Into OH minus squared, right? So this is going to be 12. So your OH minus continuum is going to be OH minus squared is 4 into 10 to the power 12. That value is 2 into 10 to the power 6. Right now, this will lead you to the right moles of electrons, right? Finding moles of electrons and charge, right? So OH minus concentration will lead you to the number of moles of OH minus. That is the concentration into volume. The volume is 100. That is just 2 into 10 to the minus 7. Right now. So number of electron moles are equal to same number. Electron moles are equal to same number. Why is it? Because electrons to OH minus is coming up with 1-to-1 ratio, right? Right here. 1-to-1 ratio when it comes to the cathodic reaction, right? Then how to come up with the Q? Now Q is NF equal to NF, right? Number of moles of electrons, that is 2 into the power minus 7. Faraday's constant is 9,600. Coulombs mole, that is something like, right, 2 into 96,400. 1.93 into the power minus 2 coulombs. So then we can use the Q is equal to IT to compute time. So Q value is 1.93 into the minus 2 coulombs. I is 1 milliampere to the minus 3 amperes into T. So the time is then going to be, right, 19.3 seconds. Right now? Okay. So just complete the stuff. Right now. So from this one, we'll wind up for today's work, and you can do the question number 7 and 8 at home. Right? I'll send you the answers. Right? So just do the two questions 7 and 8 at home. Right? So just complete the note here. Right? Complete the board, and then you can leave then. Right? I'll leave the board here. Right? Goodbye then. Good night. See you next week.